In this video, we'll continue our lecture on test of significance, and let's now get into a generalized process, because as you've seen in the last 3 videos, there are a lot of ideas, a lot of terms, a lot of stuff going on. So let's try to turn it more into a methodical process that's a little bit easier to follow. So whenever we're doing a test of significance, you can always follow this 4-step process. So you can always state, well, what is the practical question that, why are we doing this in the first place? And in these chapters, it's just, I'm giving you examples. Later on, it's a little harder. We'll kind of talk about how do you figure out which test to use. But the plan is to identify the parameter, aka mu, state the null and alternative hypothesis, so figure out what's h sub 0 and h sub a, and choose the type of test that fits your situation. And what that's saying is, like, are we using a one-tailed or two-tailed, upper or lower? So to solve that, it says to carry out the test in 3 phases. Number 1, check the conditions. So essentially, this will come back to later, but do we want to use a z-test or a t-test or something else? Again, save that question for later. Number 2 is calculate the test statistic, find the p-value. So in the last video, we did this all by using the applet, but if we were doing it by hand, it's just by using a z-table, just as we did in chapter 3, and it's going to be the same basic strat that we've been doing for a few classes. And finally, after everything, conclusion. What's our conclusion based on everything we've done so far? And so the next question is, what's the test statistic? What is that? But essentially, it's finding a z-score. And it says, a one-sample z-test for a population mean. It says, draw an SRS of size n from a normal population with unknown mean and standard deviation, a known standard deviation, to test the null hypothesis that mu has a specific value. So again, say we're setting up null, h sub 0 is equal to mu 0. So if you're wondering, what is mu sub 0? That is just our established claim. So in the first example, it was 70% is mu 0. And in the second example, it would be 550. But it's just whatever number, we're going to put some number right here, and that's mu 0. Now, the test statistic, what it says is z is equal to x bar minus mu 0 divided by sigma over root n. But what I wanted to point out is, notice this is exactly the same as a z-score. It's you take your score, subtract from the claimed, basically we're always operating under the assumption that the claim is true. And that's why we're assuming that the true value of the population is mu 0. Our sample is evidence against that. It's kind of like, going back to, sorry, wrong thing. This example right here, the mu is the mu 0, the claim 550 in example number 2. X bar is different from that. So we're trying to find the z-score of that. And the standard deviation is sigma divided by root n. And if we really look at this formula, excuse me, that's exactly what it is. X minus mu over sigma. But basically, this is just calculating the z-score, changing our parameters to the given situation. And it says, in terms of the variable z having a standard normal distribution, the p-value for the test against it. Well, so notice that it's separating this into 3 cases. If we want to check the alternative hypothesis being less than that, we could just find the probability on a standard normal z-table, because that's always what it will tell us. And we can find our p-value just by doing exactly that. If we wanted to find the probability that p is greater than the value, we need to subtract it from 1. Because if we look it up in a z-table, we're going to get this area over here. And, basically subtract it from 1. And then in the case when it's two-tailed, so, on the case that our alternative hypothesis is just that the average is different from the established mean, we need to double it instead. Because again, we need to include the possibility of our probability being less than the established mean by a particular margin, but also greater. And doubling that is how we solve the conundrum of using a two-tailed test. And we'll get into specific examples of this in a minute. But let's return to example 2 and try to do all of this by hand. So let me go back to the notes. So, let's say we're going to use table A, which is just what our book calls the z-table, to find the p-value of this test of significance from the GMAT example. So again, our null hypothesis was that mu was equal to 550. And our alternative hypothesis, let me just write that there too, because this will matter, was that the mean was less than 550. And, again, we have all these parameters. And these parameters are needed for the test. And sorry, for some reason, the quality of the image on the handout came out pretty poorly for some reason. But basically, say we wanted to know what is the z-score for this. Well, we could just use the formula. So let me copy down the formula. Z is equal to x bar minus mu naught divided by sigma over root n. But if we plug in all that, in the second case, she obtained a sample of 528 as the mean of her 100 test takers. And that was quite a bit different than the claim that they had an average of 550. And so if we want to check the validity, we could figure out the z-score for all that. And if we divide it by sigma over root n, again, we've already calculated that to be 11, but it's just 110 divided by the square root of 100. Notice what we get is just a z-score, the difference of the two things divided by the standard deviation. And what that would give us is negative 22 divided by 11, or negative 2. So again, what we would get is a z-score here, which is consistent with the, marking on our normal curve from 2 videos ago. But if I want to find the probability of this occurring, I could go to the z-table and look it up, right? So if I figure out a z-score of negative 2, as is what I have right here, right? Then I go to the table, look up the p-value, and notice what I get: a p-value of 0.0228. And that's exactly what we got when we ran it through the applet. So that's our z-score, and to get our p-value, that would be 0.0228. Or again, if we write that as a percentage, we could just write that as 2.3%. But my point is, if we want to actually do the math for ourselves, it's just normal distribution math, all the same thing we've been doing. And it's consistent with what we got from the applet in the last video. And it's consistent with just the basic 68, 95, 99.7 rule. Similarly, say we had a score that did not fit exactly along with a normalized curve, we could figure out specifically the z-score of that. And also, we just called the z-score the test statistic. So after we've attained our sample, we obtain an x bar. That is our sample statistic. To get our test statistic for that, it's just called that for the z-score of the given sample. Again, a lot of terms. A lot of notation in that case is not too different. But let's say we wanted to know what's the z-score for a 524 sample mean. Again, doing all the math, that's not going to come out exactly evenly, because that would be a negative 26 over 11. And we could toss that into a calculator to see what that would be. So let me go over here and do that. 26 divided by 11. And that is about 2.36. And remember, we want to round that. If we're going to be using a z-table, we want to round that to the nearest hundredth, because that's all we can do. And again, that should be negative. Sorry. Don't forget your negative. That will mess up your stuff. And if we go to our z-table to negative 2.36, we got 0, 1, 2, 3, 4, 5, 6. Should be right there. We should get a p-value of 0.0091. Which is, of course, approximately 0.9%, the same answer we obtained with the applet. And if we were to use a calculator, again, going to get the same answer, assuming we did everything correctly. And again, this would be basically, if your alternative hypothesis is that the mean is less than 550, it's all exactly the same, because we want to figure out the probability that we obtain a sample smaller than a particular margin. But you can get this idea from the same as from chapter 3, is that if we wanted to know what's the probability that it would be larger, we'd get the opposite probability, because we need to figure out what's the probability of it being greater than a particular margin. Or if it were two-tailed, we need to double the result of the lower-tailed test. And that's what question 15 from our notes asks is, well, what if the researcher had not had a prior inclination that her students would do worse than average and just wanted to see if her students generally differed from the average? So if we go back to that example, remember that in the example number 2, as it read, she thought that her students would do worse than 550. She already, and that's what influenced our alternative hypothesis to be in the first place. But let's say she didn't really know. She just thought, well, her students, they are not 550. Maybe they're worse. Maybe they're greater. We would change our alternative hypothesis to being mu is not equal to 550 instead of being less. And all that means is at the end, after we do everything, we'd actually need to double the probability, because it's very, very unlikely that they'll be lower. But there's also a chance that maybe the sample mean was a lot higher than 550. Like maybe it's 570, maybe it's 580. Again, who knows? We don't know because we don't know all the data. That's always why we have to do a confidence interval or a test of significance, because a sample does not always give us accurate results. And we have to take that into account. That's the purpose of chapters 16 and 17. But let's say, again, maybe this was a fluke. Maybe she takes another sample and their average is 570, right? So who knows if it's higher or lower? Then we need to take that also into account as the probability instead, because we know the probability of it being that small is 0.9%, but it could also be that much larger. And so we would need to double that. So essentially, if we were doing a two-tailed test using an alternative hypothesis, all we need to do is double the p-value after all is said and done, and that would give us a 1.8% chance. And so you can see how that does affect the margin for the significance level, because if we were using a 1% significance level, a one-tailed test is significance evidence, but on a two-tailed test, that actually would not be sufficient evidence at an alpha level of 1%. And that's something you don't want to forget. And also similarly, remember, if you are changing an alternative hypothesis to being greater than something, the issue is when you do the p-value, you're going to get like 99% or whatever, and you're going to have to subtract it from 1, as I was saying, because if you're trying to do this case, when you look it up in the p table or in the z table, but again, try to sketch out your situations, make some common sense, because it will help you to remember these sort of facts. Like, do I need to subtract it from 1? And with a two-tailed test, you need to double it. This is something that we have not had to do before, but hopefully you can see why that is useful. So the next example, I have some more videos. We'll do a fresh example, kind of restart everything, because if you are feeling a little bit lost and confused, that is normal because there's so many terms, so much going on. But yeah, to try it yourself, go ahead and try this on your own and see if you can figure these questions out. And if you're stuck at all, again, I have some videos going through every step of the way.